Okay, welcome to first lecture of Unit 2. We're going to go ahead and keep on numbering them. It's lecture 15. We're going to be looking at chemical equations. Okay. In other words, on this side of your equation you have reactants, then you have an arrow, and then you have products. It really is that simple. Your reactants over here, they combine with one another in the ratio given. They don't disappear, but the atoms rearrange to make your products. Okay, remember your conservation laws. So you're going to have your conservation of mass in particular. Every atom on the left-hand side will end up on the right-hand side. Every atom on the right necessarily came from the left. Nothing appears, nothing disappears. If you wanted to read this like a sentence, you absolutely could, and you could say yields when you get to the arrow. In other words, your reactants yield your products. Or to look at this chemical reaction, calcium carbonate goes to calcium oxide plus CO2, or calcium carbonate yields calcium oxide and carbon dioxide. Now, to make it slightly more concrete, not entirely concrete, you have 2A plus B yields A squared B. Okay. This right here is a coefficient. Okay. All of these numbers have coefficients. It's just that the number 1, oops, that's awful, is invisible. Okay. We tend to leave the number 1 out, remember? We do that for coefficients just as we do for our subscripts. Okay. Here are our subscripts, a 2 and another invisible 1, just as before. So what this reaction tells us is that A reacts with B in a 2-to-1 ratio to produce 1 molecule, or if this were a salt, 1 formula unit of A2B. Okay. So it's a 2-to-1 ratio. And that's going to be true every time this reaction occurs. Now this works for moles, it works for molecules, it works for atoms, and it works for those formula units, for salts. It does not work for mass. Okay? Mass cannot be fed into this reaction in that way. Okay? Now, an important note for the subscripts. I've emphasized this before. I'm going to emphasize it again. Do not change your subscripts ever. Okay? When you change the subscripts, you're changing the substance. Changing the coefficient is perfectly valid. Okay? This is very important when it comes to balancing chemical reactions. Okay? I've met a number of people who thought they could balance a chemical reaction by changing the subscripts. What they end up with might be balanced, but it's not the same chemical reaction because it's entirely different substances. Do not ever change your subscripts. Only change your coefficients. Okay? Chemical reactions can frequently contain more information than just the substances involved. For example, going back to the calcium carbonate, limestone, it will decompose into calcium oxide and carbon dioxide, but it doesn't just happen willy-nilly, otherwise the state of Florida wouldn't exist. It's limestone, mostly. All right, so what you need is you add heat. Okay? So when you see that triangle, that's Greek letter delta, over the arrow like that, it means you're adding heat. Sometimes they can get more specific. They might say it occurs at 180 degrees Celsius. Okay? Or you might have something like ethane, C2H6, goes to form C2H4 plus H2. That's ethene, just forming a double bond. And that might happen in H2SO4 at 180 degrees Celsius. In this case, H2SO4, sulfuric acid, is there. It's necessary for the reaction to occur, but it's not really taking part in the reaction. It's part of the conditions of the reaction. So what these all have in common is that we're putting them above or below the reaction arrow. Okay? That's where we put our reaction conditions. Anything that is really vital for the reaction to take place. We also frequently include additional information, and that additional information can subtly or dramatically change what sort of reaction you're looking at. Or not necessarily what sort of reaction, but it can change the reaction is what I'm trying to say. So for example, hydrogen plus oxygen yields water. Okay, so we'll go ahead and balance it real quick. Now, hydrogen is a gas, oxygen is a gas. Now, when you ignite this, you fire off the explosion, what you're going to get is gaseous water, just because you've also liberated a lot of heat. Okay. But it is, possible, if you control the conditions precisely, if you use some sort of catalyst, say, instead of getting gaseous water, you can get liquid water, and this would give you more heat, or, to make it more general, energy. This is what they do or they're trying to do in hydrogen fuel cells to try and make electric cars more feasible. Instead of running on gasoline, they'd be running on hydrogen and just making water instead of making CO2, carbon dioxide, that is to say, greenhouse gases. But you don't want to produce gaseous water necessarily. It'd be better if you could produce liquid water because you get more energy. Oh, I'm sorry. That's the letter Q. I don't know if that was necessarily clear. So these right here are sort of additional subscripts that tell you about the state of matter of the substance that you're looking at. So it could be solid, or liquid, or gas, or very frequently you'll see AQ. Okay, AQ, in parentheses, means aqueous. In other words, the substance has been dissolved in water. Okay? Dissolved in water. That doesn't necessarily make a huge difference. Sugar, C6H12O6, it's going to be pretty much the same whether it's solid or dissolved. The same is not true of sodium chloride. Sodium chloride as a solid is, that white substance. It's a whole bunch of ions bound together. But sodium chloride, when it's dissolved, is actually a whole bunch of free ions floating around in solution. Okay? It's very different. So remember, that's why it conducts electricity. Okay? So it's still the same substance chemically, but its physical properties have changed in a very dramatic way that doesn't occur for a molecular substance like sugar. So it's just something you really need to pay attention to. Now let's go ahead and talk about balancing chemical reactions. What you always need to keep in mind is the laws of conservation. They will be your guide in making sure that you've done this correctly. Because whatever you start with is whatever you end with. So mass and charge are what you really need to focus on for this. The conservation of mass and the conservation of charge. So whatever mass, whatever atoms, I should say, you have on the left-hand side in the reactants, you should have in the product side. Okay, that's how you'll know when it's balanced. For a lot of reactions, balancing charge isn't as vital. It's necessary, but it's easy. For some reactions that we'll be getting into a little bit later, it's a little bit more difficult, so it's something you should pay attention to. It's just another way to double-check your work. In the meantime, let's go ahead and walk through some examples of how I balance equations. Now, if you have a really good head for numbers, maybe you can juggle, the half dozen or so numbers that it's necessary to juggle when you're balancing equations. I do have a good head for numbers, but even so, I prefer to do the bookkeeping right there on the page. So let's look at the combustion of octane. So combustion means you take something, you react it with oxygen, and you get a couple of oxides on the right-hand side. Okay. So when I say bookkeeping, what I mean is CHO. I keep track of all the elements as we go along. So on the left-hand side, we have 8 carbons, we have 18 hydrogens, and 2 oxygens. Over here on the right, we have 1 carbon, we have 2 hydrogens, and this is something you'll need to be careful of. We have oxygen in 2 molecules. So it's going to be, getting changed more often. And you're going to need to add and multiply and things like that. So there are 3 oxygens on the right-hand side. For something like this, I suggest leaving oxygen till the end. You don't have to leave oxygen till the end all the time. It's just that it is a free element. So it's something that you can alter all by itself over here on the reactant side. So that's why I suggest leaving it till the end. All right, so let's start with carbon. Okay. We have 8 on the left, we have 1 on the right. So let's go ahead and put an 8 in front of carbon dioxide. That's going to alter carbon, make it 8. That's good, that's what we like. But it's also going to alter oxygen. So 8 times 2 is 16. So let's go ahead and clear that off. Just remember you're multiplying, so boom, 16. Plus 1, 17. Okay, so 16 from the CO2 here, and then 1 more over here on water. Now, let's go ahead and balance our hydrogen. We have 18 on the left, so 2 times what is 18? 9. That gives us 18. And that means we have 8 times 2 is 16, plus 9 times 1 is 9. 16 plus 9 is 25 oxygens on the right. So now we need some number n, such that 2 times n, because there are 2 oxygen atoms in each molecule, equals 25. That doesn't really work. Reason being, we have an even number of oxygen atoms. But there is kind of a shortcut. Okay? You just, divide both sides by 2, you get n equals 25 over 2. What you can do, let's clear off that space, is you put 25 over 2 right there. This is not kosher. Okay? We cannot stop here. Okay? No. You're not allowed to have fractions in your balanced equations. There is one exception we'll see, but that is a very special exception. But here, just be aware, you're not allowed in your regular balanced equations, you're not allowed to have fractions. But this is an intermediate step. We're heading along the way to finishing this problem. What we're going to do is we're going to multiply everything by 2. So we have an invisible 1 here in front of octane, so it becomes 2. 25 halves becomes 25. 8 becomes 16. 9 becomes 18. And now let's see what that does to all these numbers. Well, 2 times 8 is 16. 2 times 18 is 36. 25 times 2 is 50. Now we come over here to the right. 16 times 1 is 16. 18 times 2 is 36. Now for oxygen, this is where, being willing to write things down comes in handy. 16 times 2 is 32. 18 times 1 is 18. 16 times 2 is 32. 18 times 1 is 18. 32 plus 18 is 50. So everything is balanced out, and we have nothing but whole numbers. It looks a little bit messy, but frankly, I'm okay with that. Okay? Better a messy paper than a wrong answer. I'm not going to delete that. I'm going to leave that in. Sounds really nerdy, but just going to leave it. All right, let's keep going. Let's try another combustion. C6H12O6, that's sugar. Let's go ahead and make it a solid. Plus oxygen, gas, goes to form CO2, gas, and H2O. And let's make that a liquid, just because. Notice, go ahead and notice that I'm leaving blank space in front of each of the substances here. That's really the only way to make sure that you can put in numbers later. Otherwise, it gets really cramped and you're sort of squeezing things in and, whatever. CHO. Now we have 6 carbon and 12 hydrogen, and 6 plus 2 is 8 oxygen. And over here on the right, we have 1, 2, and 3. Okay, so let's get to balancing. Go ahead and start with CO2, why not? So let's make it 6. So that gives us 6 carbon. And then 12 plus 1 is 13 oxygen. Now, I've noticed in the past that a lot of people really do get tripped up by trying to multiply and add and things like that. So if you have to, just go ahead and start scratching things down. Put a line and say 6 times 2 is 12, plus 1 is 13. Feel free to make your paper messy. There's always the opportunity to rewrite the darn thing later. Okay. Now let's go ahead and balance out hydrogen. Let's go ahead and put a 6 there. So 6 times 2 is 12. And now we have 12 oxygen from CO2 plus 6 gives us 18 over here on the right. Now this is where people might get tripped up. We have 6 oxygen from this plus some number times 2, because there's 2 oxygens for every molecule. 2 oxygen atoms, I should say, for every molecule of oxygen. So we're trying to find the number to put in front of molecular oxygen. So this is going to be the total number of oxygen atoms. We want it to be equal to 18. That's the number we have on the right. So 2n equals 12. I just subtract 6 from both sides, then divide both sides by 2, and we get 6. So 6 times 2 is 12, plus 6 is 18. And that is the combustion of sugar. 1, remember, invisible 1, sugar molecule will react with 6 oxygen molecules to produce 6 carbon dioxide molecules and 6 molecules of water. Now let's step away from combustion for a little bit. Let's look at the Haber process. Okay. This was invented by a German dude named Haber. What he did was he looked at the combination of nitrogen and hydrogen to produce ammonia. This was one of the early green revolutions, as they're called, made it possible to produce fertilizer, really amped up the production of food all around the world. So we have nitrogen and we have hydrogen. And that's it. So we have 2 nitrogen on the left, 2 hydrogen on the left. We have 1 nitrogen on the right, and 3 hydrogen on the right. Now, if you're really good at numbers, then this will help you. If you hate math, then don't pay attention to this next, 5 seconds. But because we have even numbers in the subscripts here, you're always going to have even numbers of nitrogen and hydrogen on the left. Which means you're going to need to find a way to make these even on the right. And the way you do that is you throw in the number 2. Multiply anything by 2, you're going to get an even number. So this gives us 2 nitrogen on the right and 6 hydrogen on the right. So now nitrogen is balanced. All we need to do is fix hydrogen. And the way we do that is throw a 3 in front of hydrogen, because 3 times 2 is 6. And thus, the Haber process is balanced. 1 molecule of nitrogen will combine with 3 molecules of hydrogen to produce 2 molecules of ammonia. Now, let's look at the reaction that takes place inside of airbags. What we have here on the left is sodium azide. There's really no way you would have been able to name that. But that is a solid ionic compound that is fairly unstable. And they keep that inside of airbags because with a little spark, it'll turn into sodium and nitrogen. In other words, it releases a large amount of gas, and gas is much larger than solid. So let's go ahead and clear off our workspace so that we can get in A and in. So we have 1 sodium on the left, 1 sodium on the right, 3 nitrogen on the left, and 2 nitrogen on the right. For those of you who are good with the numbers, remember, you need even numbers for the nitrogen, so let's go ahead and double this. Turn this into a 2 and this into a 6. Now, we just need more sodium on the right, so double that, makes it 2. And we also need more nitrogen, so we triple that. 3 times 2 gives us 6. And that is the balanced reaction that takes place inside your airbag if you've ever had the misfortune to get into a fender bender or something more serious. It also releases a great deal of heat. So, and it's definitely not something you want to do even if you don't care about your car. You can get some fairly unpleasant burns from a rapidly expanding airbag. Better than dying, better than broken bones, but not fun. Definitely not fun. So what this tells us is that 2 molecules of sodium azide, if you give it a little spark, oh, that's a terrible lightning bolt. Let's try it. There we go. If you give it a little spark, let's make it, there we go. Now that's a lightning bolt. Okay, give it a little spark, and 2 molecules of sodium azide will decompose into 2 molecules of sodium and 3 molecules of nitrogen. Now let's look at a special class of chemical reactions. Ionic reactions, or double displacement. Okay. That's when you have 2 ionic compounds dissolved in water, okay, and you mix them together. So you have AB plus CD, and they swap partners. So AD plus CB, okay, so A gets with D, C gets with B. They swapping partners, hence double displacement. Now, we want to try and eliminate as much clutter as possible. So we really only want our chemical reaction, our balanced chemical equation, I should say, to contain useful information. So let's go ahead and look at a real example. Let's try sodium chloride plus silver nitrate. Okay, both of these dissolve readily in water, so they're both aqueous. They swap partners, and you end up with sodium nitrate and silver chloride. Now, sodium nitrate is perfectly soluble in water, no problem there, but silver chloride is insoluble. Okay? This is what's known as a precipitation reaction. We'll get into that more later in the chapter. Now, the thing is, let's go ahead and expand this. Okay? We expand this out into the complete ionic equation. Okay. Call it the complete ionic equation because it's going to include all the ions. But what I mean by expanding it is that we're going to break apart all these dissolved ionic compounds. Remember, I said earlier, when it's dissolved, then you have the free ions floating around in solution. So what we really have is sodium 1 plus chlorine 1 minus plus Ag 1 plus nitrate 1 minus, going to form sodium 1 plus nitrate 1 minus plus silver chloride. Okay. Remember, silver chloride is a solid. It's not in solution, therefore it's not, free ions floating around in solution. What you'll notice is you have sodium and nitrate floating around as free ions on the left, sodium and nitrate floating around as free ions there on the right. And they're useless. Okay? They're not participating in the reactions. They are what are known as spectator ions. They're just watching. They're in the stands. Okay? So that means that we are going to get rid of sodium and nitrate. Anything that appears on both sides, you get rid of. Anything that is the same on both sides of the arrow is gone. You get rid of it. Okay, we don't want them. Get rid of the spectator ions. And now I've completely run out of room, so let's go ahead, and here we're going to write out the net ionic equation. Okay. So we've gotten rid of our spectator ions. All we're left with is silver 1 plus aqueous plus chloride 1 minus aqueous goes to form silver chloride solid. So this is the net ionic equation. Remember, net as in net profits or something. After you get rid of your expenditures, okay, things like that. So in this case, net means you've gotten rid of the dead weight, the spectator ions. So let's try another example. Let's do potassium hydroxide aqueous plus iron 3 chloride aqueous goes to form potassium chloride. Let's go ahead and balance this while we're at it. Aqueous plus iron 3 hydroxide solid. Okay, we go ahead and we expand this out into the full ionic equation. That's 3 potassium plus 3 hydroxide plus 1 iron 3 plus 3 chloride 1 minus. Note that change there. The subscript on the chlorine has become a coefficient. That's just what happens when you have ionic compounds dissolving in solution. Okay, so another example, let's say it also works for acids. So phosphoric acid, you dissolve it in water, becomes 3H plus PO4 3 minus. Okay. Now we've cleared up our space. We continue. 3K plus 3Cl minus plus iron 3 hydroxide. Okay. So now we have our spectator ions, the potassium and the chlorine. So we get rid of those, and what we're left with is iron 3 plus 3 hydroxide anions, aqueous. I don't always put the aqueous in the complete ionic equation. I should, but it's a real pain in the keister to write AQ half a dozen times. All right, goes to form solid iron 3 hydroxide. And thus we have our net ionic equation. And one more just for the road. Sodium hydroxide plus hydrochloric acid goes to form sodium chloride plus H2O. This is the neutralization of acid and base. So AQ, liquid. All right. So, we go ahead and we expand this sucker out. Na plus OH minus plus H plus Cl minus goes to form Na plus Cl minus plus H2O liquid. So sodium 1 plus and chloride 1 minus are the same on both sides of the equation, so they get canceled out. There are spectators, leaving us with hydroxide plus hydronium yields water. AQ, liquid. And I'm feeling saucy, so I'm going to throw in another example. Let's see. Sodium chloride plus potassium nitrate. AQ goes to form sodium nitrate and potassium chloride. And we go ahead and we expand this out, and we have Na1 plus Cl1 minus plus K plus NO3 minus yields Na plus NO3 minus plus K plus Cl minus. Whoopsie daisy. No, this isn't a mistake on my part. I was wanting to show you that everything cancels out. And this is an example where everything is a spectator ion. So we'd say NR for no reaction. And that does it for this lecture. There will be no more talk about... Okay, there will be plenty of talk balancing reactions. Balancing chemical equations is super duper important. So remember, yes, you can change your coefficients. No changing subscripts. And anything that appears unchanged on either side of the arrow gets tossed. All right, I'll see you in the next lecture.